to Julio Villafuerte from Centerline. He's going to be talking about historical aircraft airworthiness. So with that, Julio, if you're ready to take it from here.
Yeah, I'm ready. Let me see if I can share my screen. Sure.
Got it.
Got it, so everybody can see it. Okay.
There you go.
Okay. Got a little.
Is that you inside there?
Yeah, all right, so good afternoon, everyone. I see that we have close to 500 participants, which is pretty good. So I want to thank CSAT, particularly Big, for inviting us to participate in this first virtual gathering of CSAT. I think it's great. It's got challenges. Today I'm going to spend the next 10 minutes to describe a practical, straightforward, simple repair, all facilitated by the capability of cold spray technology. And this is, as Big mentioned, this is the cold spray technology keeping historical aircraft airworthy. Before I do that, I'd like to spend a couple of slides with the company. Centerline is a privately held Windsor, Ontario, Canada-based organization established in 1957. We have over 40,000 square meters of manufacturing space in 4 facilities in Windsor, and expertise in a variety of processes, including resistance welding, gas metal welding, metal forming, mechanical assembly, and of course, cold spray metal consolidation. We have global reach with a number of affiliate offices and sales offices around the world. So since 2003, we've been in the business of cold spray. We created what we call Supersonic Spray Technology Division, SST, to keep innovating downstream injection cold spray systems, sometimes referred as low pressure cold spray. So we have a number of products that many of the attendees probably are very familiar with. We also put together integrated standard turnkey solutions. We also do integrated custom solutions. We also make our own cold spray grade powders. We provide accessories, consumables, and spare parts to support our products. We have a shop in which we use to do process development and qualification, and we, from time to time, also offer job shop services. So here's a picture of the range of products that we have, just to name a few. So today I'm talking about historical aircraft. This is what is called the Chipmunk DHC-1 aircraft, named after the squirrel. I don't know what the similarities with the squirrel are. I suppose it's pretty fast and very maneuverable. This is a post-war vintage aircraft developed in 1946 by de Havilland, Canada, now part of Bombardier. It's a single-engine tandem aircraft. There's hundreds of these aircraft in the world, used primarily as trainer aircraft. Of course, the issue with that, as many of you know, is that spare parts for these aircraft are either scarce, price prohibitive, or not possible to repair using conventional techniques. Therefore, cold spray comes into place. So the particular problem, we have these DHC-1 aircraft, number 54 aircraft, that show engine oil leak. So according to the Transport Canada approved Canadian Historical Aircraft Association maintenance manual, it was required to do a liquid penetrant and non-destruct testing to determine what was the source of this leak. In the engine, the upper cover was tested as a magnesium cast alloy, as well as the lower crankcase in the flange and the bow regions, in both cases. So what the liquid penetrant inspection showed was that there was a crack present at the flange in the upper cover, eradicating fastening point to the lower crankcase. There was also a crack present at the bolt region in the lower crankcase. Both of these materials, magnesium and aluminum cast alloys, would not tolerate elevated temperature repair processes such as welding to perform this type of repair. Therefore, it was essential that this was done by cold spray. So the SST group did an assessment of the problem, and it was determined that due to the already weakened material condition, both the cracked flange at the cover as well as the cracked region of the lower crankcase should be completely removed. The missing feature will be rebuilt using the SST cold spray process using a free form hand spray process. We worked with Transport Canada and Fleetline to design a new repair procedure because there wasn't any repair procedure for this. The new repair procedure was based on the NIL standard 3021 for non-structural repair, and as everybody knows, this is a document that was developed by ARL, Vic Champagne, and his team initially in 2008. So there's a lot of good information, good guidance to develop new procedures in this document. We decided that there was the need to simulate this freeform hand spraying. So there was a block that was used to simulate this. Some geometries were cut, and there was basically a trial using a pre-qualified powder to do this repair. At the end of the day, Transport Canada came out with a process design repair document 1701, which goes along with a maintenance manual supplement 1701M. And what this document says is that for this type of repair, we should use a series P machine with a manual spray gun, 2 millimeters orifice using a tungsten carbide nozzle. And the procedure includes removing the damaged section, completely removing that, preparing the surface with an aluminum oxide-based grit, which we call SST G0002, to roughen surfaces. Then preform hand spray these damaged areas with the SST A0082 powder, which is basically, and I show in the next slide, aluminum oxide powder, using nitrogen, 180 psi, 12.5 bar, and 425 degrees Celsius as the gas temperature. After that, conventional machining to dimensional tolerances will be done, then a CMM dimensional verification, and then assembly of the component or the engine and release. Here's the data sheet for the powder. This is a pre-qualified powder that we call A0082. It's a mixture of aluminum, pure aluminum, and aluminum oxide, certain compositions, certain particle sizes, and so on and so forth, and some properties that are given in that data sheet that were acceptable to perform this particular repair. Here's a picture of the process. The upper cover, we can see before as spray and as machine. In the upper cover, it was interesting that the thickness of the gasket was so thin that no distortion was allowed in this particular component. So cold spray was basically a necessity here. Also, masking wasn't necessary because we could just take the component away and then put it in a spray booth and do it there. It was a little bit different with the lower crankcase. The lower crankcase will have all the engine components in place. So in order to avoid tear down and disassembly of the engine, we'll have to use some type of masking. Also to protect the engine components during spraying and post-machining. And in this case, we didn't have to drain the oil from the engine. So here's the picture of the before as spray and as machine status of the lower crankcase and the region that the crack was found. At the end of the day, we put the engine together, and then we put it in the shipping dock ready to be shipped to the hangar where the aircraft was. In summary, the approval process, Transport Canada, they call this an engine cover flange repair. was completed with the following documents: the Transport Canada Process Design Repair Document 1701, the Transport Canada Maintenance Manual Supplement 1701M, and the Transport Canada Approval, which is called RA 17-139. Once the repair was done, the subsequent installation of the engine into the aircraft and return to service of the aircraft was certified by AME and AMO in accordance with the Canadian Aviation Regulations Part 5, Standard 571, maintenance. After 50 flight hours, the aircraft was re-inspected without any issues. That means without any oil leaks or anything like that. So in conclusion, the SST cold spray process proved to be a practical, simple, low-cost solution for critical dimensional restoration of hard-to-fix aircraft components such as this one. Because adhesion is achieved in the solid state, cold spray is suitable for obtaining well-bonded, low-porosity, oxide-free deposits onto temperature-sensitive materials such as the ones used in this particular aircraft. So with that, and this is a picture of the actual aircraft after the repair, I want you to enjoy your flight whenever we can fly again. And thank you, and I'll welcome any questions that you may have. I'll be happy to answer them.
All right. Well, thank you, Julio. So a couple questions came in. One was, and I think you might have answered this, but the qualification authorities for historical aircraft. So is that the Transport Canada that you mentioned on your slide?
Canada is the organization that is in charge of that approval process. And then there's the Canadian.
Okay, and I guess
there was the Canadian Historical Aircraft Association, which basically have manuals and maintenance and so on and so forth that are approved, of course, by Transport Canada. And so those are the mechanisms for approval in Canada for this particular aircraft.
Okay, and a related question, what was the cause of the original cracks, and what was the testing required to qualify it, other than presumably adhesion and the stuff that's in MIL standard 3021?
The first part of the question, the cause, I don't really, we didn't really determine that, and I really don't know what the cause was. The fact was that there was a crack, and it was very difficult to repair. So the cold spray with the pre-qualified material that was recommended for that was found to be the way to do it. So this was a completely new procedure for repair, and the acceptance criteria was based on the data sheet of that powder, because that powder has been tested for hand spraying and has been pre-qualified, giving those properties of density, adhesion, hardness, and so on and so forth. That was sufficient to go ahead with the repair.
Okay, well, I think that takes care of all the questions. Thank you very much. And we're going to move on now to Tim.